natural thing to do, I guess, is given any function, we would always like to be able to talk about its derivative, provided, of course, the function is differentiable. So, for example, a typical question that one might ask is find dy dx if y is inverse natural log x. Again, this works the same way as it did for the inverse trig functions, for the inverse of everything that we've done so far in this course. We start with this particular relationship and right away translate it into that which we're more familiar with, namely we translate y equals the inverse natural log of x into x equals natural log y. Now you see, again, since I know how to differentiate log y with respect to y, the derivative of natural log y with respect to y was by definition 1 over y. From this relationship here, I can find that the x dy is 1 over y. Okay? And knowing that the x dy is 1 over y, using my inverse function general theory, that tells me that to find the derivative of y with respect to x, all I have to do is invert the derivative of x with respect to y. I wind up with the fact that dy dx is equal to y itself. In other words, the inverse log x function is characterized by the fact that it's its own derivative. In other words, it's a non-destructible type of function with respect to differentiation. This is a rather powerful property. You see what this thing says? It says that the derivative of y with respect to x is y itself. By the way, just as an aside, we can do the converse of this particular problem. You see, we started with y equals inverse log x and showed that this particular equation was satisfied. Notice that if we start with this particular equation, starting with dy dx equals y, separate the variables, and lo and behold, we wind up with dy over y equals dx. And without carrying out the details, I leave this to you because it is straightforward. Notice that as we look at the left-hand side here, we hopefully will think immediately of the natural logarithm. Namely, what do we want here? The function whose derivative with respect to y is 1 over y. Again, you see what I'm saying is, notice that if we had started with this particular differential equation, we could have shown that a logarithm, and hence solving for y explicitly, would have led to the inverse logarithm also. But at any rate, notice then that we can find the derivative of the inverse log just by knowing how to find the derivative of the natural log itself, which is as we expect things should be. Again, and this is a notational thing, we do not use the language in general, inverse log x. In other words, you know, it's quite conventional to talk about inverse sine x. You may notice that sometimes in the text, sometimes in my lectures, I may have used the word arc sine x. But the general notation is sine to the minus 1. However, when it comes to the natural logarithm function, the inverse is usually not written as inverse natural log x. It's usually abbreviated, and let me say this, by the symbol e to the x. Now, the reason I say by the symbol is this. If I wanted to, I can say, look, if I've never heard of exponents before, let this symbol be an abbreviation for inverse log x. Does inverse log x exist? Yes, I even drew the graph of it at the beginning of this particular lecture. However, again, if you are tempted to use exponents, the notation e to the x is in keeping in line with the idea of our previous lecture. I say what? This matches the identification of natural log x with the log of x to the base e. Remember, in our previous lecture, we mentioned that this particular function exists without having to talk about a base. But if you wanted to identify it with a traditional logarithm, the base you would have to pick is the base e, where we showed that e was some number between 2 and 4. In other words, again, it's just like our dy dx versus dy divided by dx and other symbols that we invented this way. Namely, if I look at e to the x as being the inverse of the natural log, or whether I look at it as being e raised to the x power, where e is that number that's someplace between 2 and 4, I don't get into any trouble either way because of the natural identification of choosing e to be the base of my system. But I just mentioned that in passing. Now, you see, the rest of today's lecture will go fairly quickly. And the reason that it will go fairly quickly is that once we've established what the function is that we're talking about, every other property of that function is going to follow from the principles that we've already learned. For example,